Hi, and welcome back to our online course on testing complex intelligent systems and autonomous vehicles. My name is Daria, and I'm a researcher and a marketing communications manager with Exactpro. This is lecture 2 of the course, and today we'll give you a brief introduction into the history of autonomous vehicles and their development as a type of technology. We'll start with a few slides on the history of self-driving cars. I'm sure you all know the first autonomous vehicle ever devised. It appeared in a series of Middle Eastern folk tales entitled 1001 Nights, also known as Arabian Nights, and it was called the magic carpet or the flying carpet. The phenomenon later transpired into many other cultures. So this first prototype satisfied all the requirements of an autonomous vehicle. It was comfortable, it was safe, it got the story characters to their destination, and it required little or no human input in its functioning. But all jokes aside, the first attempts of actually creating a self-driving car date back to the 1950s. It all started with the RCA Labs miniature model that was controlled and guided by wires laid in a specific pattern on the laboratory floor in 1953. Several years later, the tests continued on a highway strip, and this is the picture you're seeing on the screens. The detector circuits buried in the pavement were able to transmit impulses to guide the car, all the while determining the presence and velocity of any metal vehicle around it. Let's take a look at another example. This time, the vehicle is not guided by the sensors installed in the pavement. You are seeing a fully autonomous car operated by a computer. The cameras installed in this automobile picked up the road markings, and the computer vision algorithms had the car travel at 30 kilometers per hour. Would you like to guess when this car was built? Take a second to think it over. And the correct answer is 1977. The car was created by the Tsukuba Mechanical Engineering Lab from Japan, one of the pioneers of computerized driverless cars. And here's one more example. In 1966, Alberto Bragi's group created the Argo Project. They took a Lancia Thema car and equipped it with vision sensors, computerized processing systems, and actuators. This early driverless vehicle covered 2,000 kilometers of Italian roads, operating autonomously 94% of the time. So this example serves to show that humankind learned how to automate driving 25 years ago. In fact, most of the tasks we face while driving can and have been automated. So what has been the challenge of pushing this level of autonomy to 100%? Public safety as well as public and regulatory acceptance have been big issues. These, however, cannot be overcome and still cannot drive the industry forward without further advances in machine learning and sensor technology. So, shall we take a look into the existing autonomous vehicle setup? The general scheme of robot, drone, and autonomous vehicle control is quite similar. There are separate sensors that need to be connected as a single network. The protocol for their communication and interchange of information has been in place for some time. It was originally developed in 1985. It's called the Controller Area Network, or the so-called CAN bus. What this implies is that the sensors or controllers communicating some information are connected to the main bus. There's also a control center that collects, processes, analyzes the information from the system and makes decisions based on this data, which as a result lets it manipulate the steering wheel, the brakes, the engine, the accelerator, and other vehicle components. As for the car's sensors, the list of sensors may include video cameras, radars, sound detectors, the one most specific to autonomous vehicles being LiDARs. The word LiDAR means light detecting and ranging, and the difference between a radar and a LiDAR is that the former sends out radio waves to detect presence, direction, distance, speed of aircraft or other objects, while the latter sends out light in the form of a pulsed laser. The continuously rotating LiDAR system sends out thousands of laser pulses every second. These pulses bounce off the surrounding objects and return to the detectors. An onboard computer records each laser's reflection point and translates it, thus updating the point cloud into an animated 3D representation. The picture you see on the screen is an example of what a LiDAR produces. Based on this information, the system can make decisions and manipulate the vehicle. Naturally, there's the question of cost. LiDARs used to be a really expensive technology just a few years ago. In 2019, a LiDAR could cost as much as $75,000 per unit, while the most recent models may not even exceed $1,000, for a high-quality LiDAR that's not bulky, that's easy to fit in a passenger vehicle, and that has no rotating parts. So let's look into the questions that the car's control center has to continuously answer. The vehicle has to understand where it is. Namely, it has to know the exact coordinates and geolocation. It has to know its position vis-a-vis the landmarks, the pedestrians, and other vehicles. It has to be able to process its surroundings, and that's where radars and LiDARs come into play. It needs to reconstruct the 3D model of the road, the street, and the traffic in which it's driving. The data stream it's receiving from the sensors is dynamic and ever-changing. So the control center has to make an informed prediction about what's going to happen next. Is this car next to me going to change lanes? Is it going to steer left or right? Is that obstacle static or dynamic? Is that pedestrian standing over there going to cross the street, or is he or she going to keep standing? The control center analyzes that and makes a decision as to steering left or right, accelerating or slowing down, etc. The slide demonstrates this cycle. The sensor captures images, the control center processes them, and commands the controller to steer the vehicle. The sensor data changes, and so does the 3D model. As they go, the control center needs to process the new data feed and make new decisions. And this brings us to another question. How fast does the car's control center have to make these decisions? Let's say a car is moving at the speed of 36 kilometers per hour. What distance would it cover in 1 second? Now, I understand that 36 kilometers per hour is not that high a speed, even for city limits, let alone a highway. But let's just imagine that we are traveling at this speed. So what would be the distance covered by this car in 1 second? Is it 20 centimeters, 1 meter, 5 meters, or 10 meters? Take a second. It's quite simple. The answer is 10 meters, and 10 meters is quite a distance, wouldn't you say? It's 2 or maybe 3 times the car's length. So if, let's say, it takes your car 1 second to make an informed decision, then the decision may come a few meters too late. It has to work more quickly than that. It should take 1/10 or maybe even 1/100th of a second. The information about the road and about the traffic is continuously updating, and the input needs to be processed in real time. So the cycle we talked about should be able to complete in fractions of a second. This brings us to another question. If the decisions a car has to make have to be made in fractions of a second, then how plausible is it that a human can really intervene? In the design of every robot or autonomous system, there's always an implied failsafe. If something goes wrong, we hope to step in time to take over and save the day. But here's the catch. A driver's average reaction time is as much as 2.3 seconds. So it may be unrealistic to assume that if a vehicle's control center makes a mistake, the human will see that, analyze it, and take the right measures in time to prevent the accident. This raises an ethical dilemma of sorts. Which tasks can be entrusted to autonomous vehicles and which probably shouldn't be? There are different classifications of how independent a decision-making system can be. This slide shows a classification related to levels of automation of decision and action selection based on the Sheridan model. The first level is when the system offers a complete set of action alternatives. The computer calculates all options and shows a human the available ones. The human then makes a decision and selects one option from the list. The second level is when a computer narrows it down to a few choices, filtering out the choices that don't suit. For example, this one is ineffective or this one is unsafe. The remaining options are presented to a human to choose from. Level 3 is when a computer suggests one single action, filtering out the rest less suitable options. The fourth level is when a computer executes a single action if a human approves. The fourth level is the veto level. That means that the computer makes a decision and provides a human with a limited time frame to veto it before it executes the chosen option. Level 6 is informing the human after the fact. At this point, the only decision-making power a human has is to shut down the system entirely. Finally, level 7 is a fully autonomous system. A human doesn't intervene and has no power to do so. The majority of AI systems being developed right now are their first or second levels, but there are level 7 systems around as well. Let's take a look at a traffic lights grid. 3 colored lamps blink in a predefined sequence, and the system itself doesn't seem super advanced. And yet it's a system that makes decisions that everybody tacitly obeys. The only thing a human can do to contradict the system is to shut off the power grid entirely. Let's say that this system is upgraded with CCTV cameras scanning the offender's license plates and sending them a traffic code violation fine. It's an example of a level 7 system, of course, because it independently scans the plates, makes a decision as to who violated the road regulations, and fines them. And there's nothing you can do about it. It's safe to assume that there's going to be more and more systems like that in place in the near future. When it comes to driverless vehicles, the levels of autonomy are also explicitly described and featured in the Society of Automotive Engineers classification. Level 0 implies no automation. Although a car can have some features limited to providing warnings and momentary assistance, like automated emergency braking and blind spot warning. These features don't propel the car, so they don't qualify as automation. Level 1 introduces a fuller range of assistance. The features could provide either steering help or brake and acceleration support. These could help you either with lane centering or adaptive cruise control. Level 2 goes a step further and offers both steering and brake and acceleration assistance. So both of these features are on at the same time. Levels 0 through 2 necessitate the driver's control even if the support features are engaged. The driver steers, accelerates, and brakes as needed to maintain safety. The next 3 levels, however, describe situations where you are not driving if the automation features are engaged, even if you are in the driver's seat. Levels 3 and 4 features can drive the car under limited conditions and will not function unless all the requirements are met. Level 3 autonomy means that if a vehicle requests so, you must take the wheel. Level 4 features will retain control of the vehicle. At this point, pedals and the steering wheel may or may not be installed, such as in the case of a local driverless taxi. Human assistance is not required, although there's still a manual override function in place. This leaves us with Level 5. The features of this autonomous vehicle can launch and operate it under all conditions. The steering wheel and pedals will be eliminated. So, how do we benefit from Level 5 automation other than having extra time to read the morning paper on the way to work? Former GM executive Lawrence D. Burns' book entitled Autonomy, The Quest to Build the Driverless Car and How It Will Reshape Our World, provides some convincing statistics looking ahead into a transformed future. So let's look at some of the facts he quotes. The average speed in congested cities can run as low as 12 miles per hour, with some of the cars being powerful enough to travel at 120 miles per hour and beyond. Less than 30% of the energy from the gasoline you put into your car is used to move it down the road. The rest of the energy is wasted as heat and sound or used to power accessories like headlights, radios, and air conditioners. Only about 5% of the gasoline energy translated into motion is used to move the driver. This amounts to 1.5% of the total energy in gasoline. American cars sit unused about 95% of the time. So using your vehicle just 5% of the time means that you have to figure out a place to store them the other 95% of the time. Plus, you obviously have to insure and maintain your vehicles and pay for the parking. In addition, paved parking lots create heat islands and may be contributing to climate change. On top of that, the emissions from cars and trucks amount to 1/5 of the greenhouse gases created in the United States. And the distance we travel by automobile is growing. These numbers alone make us believe that maybe personally owned, human-operated gas-powered vehicles cause overspends and waste a large amount of natural resources. On a separate note, accident statistics reflect a staggering number of deaths on the road. The worldwide automotive industry has recognized driver performance, that is, error in choice, as a key factor that impacts safety. The World Health Organization estimates that auto crashes around the world kill 1.3 million people a year. In 2016 alone, 37,461 Americans were killed in auto crashes, contributing to unintentional injuries, the leading cause of death for Americans in the first half of life. Many forces are at work in the automotive industry to advance safety technology. 360-degree vehicle views and rear-view video systems, forward collision warnings, lane-keeping assist systems, introducing automatic emergency braking system standards, as well as other measures. So Level 5 automated driving systems take out the human factor altogether. Their ability to perform certain driving functions automatically sounds enthralling, but there are still a lot of gray areas that require thorough testing and regulatory clarity. Within one simple 1 kilometer route, the number of edge cases, let alone typical test cases, may be overwhelming. That's why the US Department of Transportation issued a sample framework for automated driving systems testable cases and scenarios to further support the goals of improving safety for all users of the transportation network. To sum up, a lot of work is being done to increase road safety, and a large portion of it is being done in the field of advancing the safety of self-driving vehicles. Currently, not without issues, their radars, LiDARs, sensors, and cameras are undergoing transformational changes in leaps. Their testing and their safety and regulatory compliance are some of the main tasks on their providers' hands, on par with the technology issues. If you prefer to look into these and other documents in more detail, you'll find the links to all the extra sources I've mentioned in this presentation and in the description below the video. This concludes today's lecture on the introduction to autonomous driving vehicles. I hope it's been informative. If you haven't yet, then do join our Telegram channel so you can talk to your peers and the course instructors. I look forward to seeing you at the next lecture. Thank you for your attention and have a good day.